some of the
Let me think about it.
all right.
Okay, so given that this is the second meeting today, I just want to, and the population has changed a bit. Let me just go back to a few of the things that I said at the beginning. Projects. So unfortunately, I couldn't have the office hours on Monday, and yesterday there was a long line, and I couldn't see all of you. So please come again Monday, Tuesday next week, because I cannot meet later this week. If you have an urgent question, drop me an email and I'll try to respond before Monday, but otherwise Monday and Tuesday will be the next 2 days. All the dates and things you already know. I also wanted to mention that there is an exam. So as you all know, unfortunately we lost in the lottery and we got the last day of the exam period. It's not the best thing for me, for the TAs, for you, but that's what we have. I mean, we cannot change it. We cannot have multiple dates for the exam, even though some of you would like it, but that's what we have. So other than that, it's going to be structured similar to the midterm, only that you'll have more time. It's cumulative, closed books, only stuff that we covered in class, and we're going to give you some practice exams. So one thing that I wanted to remind you is that, just in terms of the focus of the exam, so the exam is on what we've done in class, sort of the learning part of the class, and as you already know, the homework is on the applied part of the title of the class. So that's about it. Questions? Okay, so let's So let's move on. So what we spent time in the last hour and 15 minutes talking about Naïve, about Bayesian learning, and specifically we finished with the Naïve-based classifier. I'm just going to remind you, where is it? So this is the example that we've run for the Naïve-based classifier. Two things that you want to note here. One is that's the Naïve-based classifier at the top right there, right? So we make a prediction as the argmax over this product, where this is the probability of a label, Vj, and this is the probabilities of a feature value, xi, given Vj. We showed that under the assumption that feature values are independent given the target, the label, this is the base optimal classifier, and then we gave an example of how to use this. So now that we know what naive base is, I want to talk about the important question of why does it work? So why does it work? Any suggestion? Guesses? So we noted that it's different than previous classifiers that we've seen. It makes predictions, but it doesn't, there's no trial and error, there's no search here, right? So it's not that we looked at some data, we tried the classifier, we saw how well it's doing, we changed something, we saw how well it's doing, and we changed something, and so on. It's not error-driven. Moreover, we don't even check for consistency. Right? We don't know whether the predictions are going to be consistent with the data that we've seen. We basically just look at the data, do some computation, and get a prediction. So the question of why does it work is important. So one observation is, if the assumptions that we're making are correct, that is, if the features are really independent given the label, then what we're doing is optimal. Clearly, that's the best thing you can do. In practice, though, this will not work, because we're going to use this classifier, which is actually a pretty good classifier. You'll play with it in the current homework a little bit. It's unrealistic to assume that the features are independent given the labels. Nevertheless, it works. So the question is why. So we're going to spend a few minutes trying to understand this. And let's start, we have to start with doing some algebra. So first of all, the key observation, or the way we presented it, let's say, is we don't give a classifier. What we gave is a procedure to make predictions. So the first thing I want to do is I want to represent it as a classifier. So when do we predict one here? So basically we predict one, and I'm talking here only about the case of Boolean labels, when 1 is more likely than 0. Or I can write it as when this product is larger than this product, right? Or the ratio is greater than 1. So we can rewrite this. So again, this is the ratio that I showed before, and I'm going to use the following notation. Pi is going to be P of xi being 1, given that v is 1. Qi is going to be the probability of xy being 1, given that v is 0. And with this notation, I can write this product in the following way. So here I'm writing pi to the xi the same trick that I used before, 1 minus pi to the 1 minus xi. What does that, how do you read this? If xi is 1, basically this product can be written as pi, because this is 1, and this disappears, it becomes 1. If xi is 0, this disappears, and what you have is 1 minus pi. So basically this is a compact way of writing either pi or 1 minus pi, depending on the value of xi, which I don't know. Okay? So exactly the same trick that I used before. So I can write it this way. I'm just copying it here, and what I'm doing on the right side is I'm dividing everything by 1 minus pi to the xi or 1 minus qi to the xi. So I can write this, instead of writing this way, I can write pi over 1 minus pi to the xi, where 1 minus pi is here outside. So far I've done nothing. I can take the log of this. What do I get? From the first part here, I'm getting log of this ratio, which is here, plus log from this ratio, I'm getting 1 minus pi over 1 minus pi, sum over all the i's. And here is the only part where xi is, because I took the log. What I get is sum over I, log of these ratios, pi over 1 minus pi, minus qi over 1 minus qi, and xi is outside. So what did I get here? How can you interpret this expression? So basically, the way we started is, we're going to say 1, we're going to predict 1 if this ratio is greater than 1. I played a little bit with the ratio, I took the log, so now I'm going to predict 1 if this expression is positive. What is this expression? What type of function do you see here? What type of function do you see here? So the pi and the qi are constants. You know, these are constant derived from the observations of the data, right? The probability of xi being 1 given that the label is 1, or given that the label is 0, and so on. Xi are the feature values, your variables. So what is this? Yes? Yeah, exactly. So this is basically a linear classifier with coefficients that are derived from the pi's and the qi's, some functions of the pi and the qi's. And then I have another free coefficient here. Still, it's a linear function. So basically what we've shown is that naive Bayes is making predictions as a linear function over the feature vectors. Something that you've seen before. I mean, it's the same type of linear functions, with one exception, that the coefficients were not driven in an error-driven way, but were just computed using the statistics over the data. That's it. In fact, and you know, there's some simple condition here for, so these are the W's that we have, if you want to think about it as a weight vector times the feature vector. So there's one other thing we can say here. So we basically show that the log of the ratio of the probabilities is basically a linear function. Now I can even write it in the following way. Because P of Vi, Vj given 1, being 1 given x, is 1 minus P of Vj being 0 given x, I can do a little bit of algebra here and write, using this same linear function, I can write the probability that I'm going to predict 1 on example x is 1 over 1 plus e to the minus the linear function. I'm writing here the explanation of how I derived this. It's just a simple algebra. But basically what we see here is that it's simply the logistic function that we've seen already before. Right? So you can either think about it just as a linear function if you want, or you can think about it as this logistic function. Either way, what we see is that naive Bayes makes predictions based on a linear function. No magic here. And really, it is a classifier. It is a classifier of the same family of the classifiers that we've seen before. And in fact, this gives a good explanation of why it works, which I'm going to summarize. So before I get to it, I want to point one thing that if you look at these coefficients here, you can see that, okay, it's a linear function, but the coefficients are constraints. And in fact, I may say it a little bit later, but I want to emphasize it here when you see it. Not all linear functions can be expressed this way. The pi's and the qi's are functions of the data that you see, and not every wi, not every coefficient can be expressed this way, which means that if you're thinking about the space of all linear functions, perceptron or SVM can basically express every linear function there is. Naive Bayes, it turns out, cannot express all linear functions. You can actually build cases where the linear function that generates the data is 1. If you look at this data and you generate and you use naive Bayes on this data, you will not be able to get this linear function because the space of linear function that naive Bayes makes use of isn't the whole space. Okay, but let's go back to give some kind of a explanation of why this works. Now that we can give several types of explanation. The first one is learning theory, right? So we've already we already know that linear models are robust because they have low VC dimensions. So if they can be consistent with the data, they're going to be good learners. This is something that we've already seen. But is there a reason to believe that they will be consistent with the data? Which, remember that in learning theory we said, let's try to minimize the empirical error, be consistent or close to be consistent. Under these conditions, if you have low expressivity classifier, everything is going to be good. So here we know that everything is going to be good because it's a linear classifier, but why would it minimize the empirical error? And in fact, in general, it's not going to minimize the empirical error, but the way people use this, which violates all the probabilistic assumptions, is they choose a set of features to express the data, they compute the naive Bayes classifier, even though the way I presented it, you don't need to check consistency. You have the naive Bayes classifier, that's it, use it. People do check whether it's consistent with the data, whether it minimizes the error. If it works, okay, we're happy, we have a good classifier. If it doesn't, let's change the features. Let's augment the set of features until we are happy with the performance on the training error. In doing it, in most cases, we are actually violating the conditionally independent assumption even more than we violated it before, because we typically add functions. We start with some set of features and we add functions of these features. So if it's even less conditionally independent than it used to be, but it's going to minimize or do better on the training data. Still a linear classifier, so learning theory is going to tell us it's going to do okay. So basically, that's the key reason why naive Bayes actually works. There is another issue which is a little bit less important and a little bit harder to argue, which actually gives a chance to naive Bayes to work, and this is the fact that naive Bayes basically is a product distribution, right? So the way we've written it is a product of conditional probability distributions. And it turns out that product distribution are actually expressive. So product distribution are what is called dense in the space of all distribution, which basically means that next to each real distribution, you can find a product distribution. So naive Bayes has a chance to approximate everything that you can do. And here's the comment that I made before, that naive Bayes classifier cannot express all linear functions. On the other hand, they converge faster to what they can represent faster than other classifiers. Okay, so we have some explanation of why naive Bayes works, and it's not the standard explanation that it so happened that the data is that the features really are conditionally independent. It really goes back to learning theory. Okay, so questions on this? Okay, so there are two loops that I want to close now. And we can do it by introducing these two questions. So one, if probabilistic classifiers are actually just like linear classifier, which I just argued, can we take the outcome of any linear learning algorithm and interpret it probabilistically? And the answer is yes, and in fact we've already commented on it. You can always scale the output to behave like probabilities. And perhaps the more interesting question is, if probabilistic hypotheses are just like other linear classifiers, can we train them similarly? For example, can we train them in a discriminative way, just like we did before, in an error-driven way? And the answer to this is also going to be yes, and we're going to see it. So first of all, this is what we've seen before, just a few minutes ago, showing the naive Bayes as a probabilistic classifier over a linear function. So the answer to my first question is actually very simple. If you look at this expression that I just showed, 1 over 1 plus e to the linear function, basically what you can do is you can tune these coefficients. So instead of looking at it this way, you can put a coefficient over this and tune it until it behaves like a probability distribution. And people do this, and there are several packages that actually do this over development set. And then the real numbers that you get from your classifier will behave like a probability distribution. The second answer, or the second question, is actually more interesting. So when we talked about naive Bayes, we said that we actually don't train it. We just take data, do some computation, we get a classifier. Can we do better than this? So let's look again at the expression that we got. The expression that we got is this logistic function. P, the probability that the label is 1, given the data and the parameters, is 1 plus e to the minus linear function. Now, this is the naive Bayes model, and this is also called the logistic regression model. Now, when we talked about it from the naive Bayes perspective, we said, let's just compute W. It's a function of the PIs and the QIs, as we showed. But in order to do this, we needed this independence assumption in order to derive this. What happens if we drop this? We don't make any independence assumptions. So let's just find the best W. into this expression. So training is going to be more difficult because unlike computing the PIs and the QIs, we'll have to work hard to find what is the best W on our data. On the other hand, it's going to be more expressive. It will not have this limitation that not all linear functions can be expressed. How do we do it? How do we drop this assumption? We've actually seen it many, many times. We have now a function which we can treat as our objective. Let's find the best W for it. So given this model, the goal is to find W and V that maximizes the log likelihood of the data. Forget any assumption. So I'm writing it again in a slightly different way, basically summing now over all my data. And this optimization problem is called the logistic regression optimization problem. Before we do it, I want to add one more thing, right? So this is just a comment that its importance diminishes with time because people forgot it, but logistic regression actually has some other interpretations. And it used to be called, at least in the NLP community, a maximum entropy model rather than a logistic regression because the resulting distribution is one that maximizes, is the one that has the largest entropy among all those that activate the same features. This, as I said, becomes less important, so let's forget this and go back to the optimization. Before we optimize, as we agreed on in the last few weeks, we probably also want to regularize. We want to add a component to this objective that will push us toward simpler W. So I'm adding this component that you've already seen before, this half of the norm of W to the same logistic function. And instead of just optimize for this part, I'm going to actually optimize for this part. And again, I'm also adding a constant, just like we've seen for the SVM case, that allows us to balance between the regularization parameters and the objective that we define. So just like before, we call this the regularization terms, and the other one is the empirical loss. And we have a new loss function, right? So it's essentially the same game that we've played before. Before we've seen L1 SVM, which looked like this. We've also commented on L2 SVM, which basically takes the empirical loss squared. And now we've defined this new one, the red one at the top, which is the logistic regression. Now, if you plot these loss functions, what you'll see that actually the logistic regression loss is very, very similar to the L1 SVM. So essentially, we're playing in a very, very similar game to what we've done before, only that we derived it in a completely different way. So again, how did we get there? We started with naive Bayes, or with Bayes optimal classifier. We made an assumption that made it a naive Bayes. The assumption was conditional independence of the features. Once we got these classifiers, we showed, by doing some algebra, that this is really a linear classifier that makes its decisions this way. It predicts based on the log of 1 plus e to this linear function, where the linear function was, the coefficients of the linear function were basically derived from statistics of the data, PIs and the QIs. So that was naive Bayes. And then we said, okay, with the same functional forms, what happens if we relax the conditional independence? If we relax the conditional independence, we have to have a way to derive the W's, otherwise. And we said, okay, let's just optimize for the W's. The same way that we've done with earlier algorithms, right? Basically, you can use stochastic gradient descent or any other optimization algorithm to find the best W given the data. So essentially what we've seen is that we have this spectrum of algorithms from very simple probabilistic algorithms that share the same functional form with these seemingly more sophisticated discriminative algorithms. Close the loop. Questions? Okay, so what we have here in the rest of this lecture, which I'm not going to talk about, is a few other naive-based examples. It's, as I said, when we talked about Bayesian classifiers, everything is in Bayes' rule, and the rest is just instantiation of it. So you've seen, you consider a few more instantiations that I will not have time to go through. Questions so far? Yeah.
Can we incorporate priors into the logistic regression formulation?
I don't know how to incorporate the priors when you use it discriminatively, but maybe there are ways. Because discriminatively, basically it's just, calculus, right? So I'm not sure how to do this, but there could be that there are ways. Other questions? Okay, so let's move on and try to build on this. Okay, so the next, we're going to build on what we've done with probabilistic classifiers and talk about an important algorithm that is called EM for expectation maximization. So before we get there, I want to remind you what is expectations. I assume you already know, but the important property of expectation that we're going to use over and over is linearity. So I'm just reminding you that the expectation of the sum of two variables is the sum of the expectations. You can think about it and recover why that is true yourself, but it's good that you'll have it at the top of your head. And let's start by talking about semi-supervised learning. So the running example that I'm going to use here is something that is called prepositional phrase attachment. So here are two sentences: buy car with money, buy car with wheels. And you can see that the word with here is different, right? So one of them is car with wheels, and the other one is buy with money. So the attachment of the preposition is different. So let's assume the problem that we have is, given a sentence, all the sentences are going to have four words and a preposition inside it. I want to predict what type of preposition is it. Is it the one that attaches to the verb, or is it the one that attaches to the noun? So I have these four attributes. I'm going to take all combination of attributes as my features, the full conjunctive set. So I'm going to have 15 features for each examples. And the examples are x1 up to xn with a label. The label is n or v for noun attachment, or V attachment. So now we know naive Bayes, we can do naive Bayes for this. What does it mean to do naive Bayes? It means to organize your statistics in two columns, the probabilities that are relevant for the noun predictions, P of n, P of xi given n for all xi's. Second column, P of v, P of xi given v. And then given an example, just remember the tennis examples that we've seen just a few minutes ago. Given an example, I'm taking the relevant probabilities. The relevant, I mean, for the xi values that I've seen, I care about these probabilities, I don't care about other probabilities, and I can compute P of n given x, the probability of predicting noun attachment given the data, and the probability of V given the data. Here's an example. I've seen 10 examples. I computed P of n, P of V, turned out to be 0.5. I computed P of, I'm showing here only for 4 features, P of x1 up to P of x4. And now, given an example, what does that mean, this example? That I care about P of x1 being 1, P of x2 being 0, P of x3 being 0, P of x4 being 0. Right? And I gave you enough numbers to compute this, and hopefully that's what you will get for Pn. So the prior is 0.5, the first one, and then 0.75, and the rest is 0.5, and the same thing you can do for PV, which probably means that you're going to predict n. Now, the key question. So you know how to run naive Bayes. If you have data, you can run it. Now the question is, in addition to these 10 labeled examples, I'm also giving you 100 unlabeled examples. What would you do? Will it help? Yeah.
It will help you approximate the data generation distribution better.
What do you mean?
So, probability of xi's could be approximated better using the labels.
But I want the probability, in order to make predictions, I need P of xi given n and P of xi given v. So I mean, the intuition is right? So it feels like you know more about the probability of xi. Maybe in all the examples, xi is 1, x1 is 1. That's important to know. But how do I use it in the context of the naive Bayes model, right? So in the context of the naive Bayes model, what I need is, as you see, there is P of xi given the label, and I don't have the label. But what do I have? I already have 10 examples that are labeled, which basically means that I already have a model. Right? So when I gave you this example, 1, 0, 0, 0, you predicted on it. So let's combine this with the 100 examples that I gave you. What can you do? Yes, I can predict on the other labels because I have a model, and then so basically now I have labels for the 100 examples, right? Because I predicted. So now I have 110 examples that are labels. But what is the problem, potential problem with this? What does that mean?
You're going to get
Errors magnify something like that. If there are mistakes, they magnify.
Yeah, so it could be that, you know, everything I did was wrong, or a lot of what I did was wrong. The labels are incorrect. I'm now learning from incorrect label. But first of all, in principle, I can do this, right? So we have an estimate for the label. So maybe I can take the estimates that I have and use them in a more clever way. Don't believe all the labels. What would you do if I ask you to still use these labels, but maybe in a more careful way?
We add a probability that
You put a weight on each of the labels that's sort of correlated to the probability of it being in that class.
What is the weight that you will put?
So if we say the probability of this example being n is, say, like 0.3, then the weight of 0.3 on that example.
Okay, so basically you're saying don't completely believe this, but try to figure out how to do it. So first of all, we want to believe some of it. For example, okay, so before that, what I can do is I can threshold, right? So the first thing, I could say, you know what, if the probability is very extreme, the probability of n is above 0.9, or the probability of v is above 0.9, these examples, I believe, probably these labels are correct. I'm going to take only this example, whatever fraction there is of the example that is extreme, throw the others. Now I have still a few more labeled examples. I'm going to relearn the model. So that's one option. The other, and this is a good option, right? So this will iteratively, I can do it many, many times. Every time I will add a few examples, the label of which I can count on. So the problem of, hopefully, the problem of adding noise to the data is smaller. But I can actually follow your suggestion here. So really, I don't necessarily have to have a label to the example. I can have a fractional label. So when I'm looking at an example, it is associated with P of n and with P of v. I can say this example is an n example, an n labeled example with this probability, P of n divided by P of n plus P of v, and it's a v example with P of v divided by P of n plus P of v. So no one said that when I do naive Bayes, I have to have labels that are integers. The labels could be fractions. So if I do it this way, essentially I'm believing more to examples that have extreme probabilities. I'm believing less to examples that have less than extreme probabilities. If P of n and P of v is a half, it basically means that I don't take this example into account at all because these two numbers are going to be identical. So basically what I have now is I added label data in a clever way. So I'm summarizing what we've done. So one way was using a threshold, right? So choose examples labeled with high confidence, label them, retrain. And the second one is use fractional examples. Label the example with fractional labels, retrain. So now let's, okay, so first of all, both algorithms can be used iteratively. I can keep on going. Both algorithms can be used with other classifiers, right? So it doesn't have to be naive Bayes. I mean, I motivated it from the naive Bayes side because it's easy. But in fact, every algorithm that gives you some confidence in its predictions could be perceptron, can be used in exactly the same way. And so this is one dominant way of doing semi-supervised learning. In fact, this is the one that you're going to use in your homework. which is the reason I'm mentioning here today. So there could be other versions. This algorithm that we just talked about can be also viewed as some kind of a bootstrapping algorithm. You bootstrap your algorithm with a small set of labeled examples. There are other semi-supervised algorithms. Many of them are graph-based algorithms, where the idea is that you can think about your examples as placed as nodes in the graph, where edges represent some kind of similarity. And the goal is to label even nodes that come without labels as a function of how similar they are to examples that are labeled, where the idea is that similar examples deserve similar labels. So we're not going to talk about this family of algorithms. We're going to continue with the semi-supervised algorithm that we just talked about before, but I'm going to ask the following question. So what happens if instead of the 10 labeled examples that we started with, we now start with 0 labeled examples? Yeah.
I have a question.
Yeah.
So the effectiveness of this approach is directly related to how closely your labeled examples are able to approximate the actual label space description, right? I mean, the better they are able to approximate that description, the better the performance.
Or you could say, how good is your initial classifier? Because if your initial classifier is very good, when you label the unlabeled examples, you labeled it correctly, so you have good labeled data, and you can continue this way. So if your initial classifier on the 10 examples is lousy, you're going to add noise, and in fact, you're going to move away from the correct. And this will happen, right? And this could happen. So there's no guarantees with these kind of algorithms unless you make a lot more assumptions. And even in the homework, you will see that depending on how you filter, you may not improve at all. In fact, you may degrade your performance.
The weights we associated with all the unlabeled examples, they were not a function of the classifier, right? They were like just the probabilities of seeing that label in your labeled examples.
No, not exactly, right? So there were this P of n divided normalized. Right. So if you know how to estimate your confidence well, it's going to be good. If you don't know how to estimate your confidence well, it's not going to be good. So and yeah, I mean that's really so if you start well, you can continue well. If you start badly, you will not continue well. Really, this algorithm hinges on making correct assumptions, if you want. And we'll see this in a few minutes, or in fact, maybe next time. But at least we'll motivate it today, that making good assumptions is critical here. But let's continue here. So we started with 10 examples, we developed an algorithm. You agree that we can take this model, the outcome of this algorithm, and use it to improve, if we're lucky, to improve the model using this 100 unlabeled examples. Now I drop the 1. It's not 10 labeled examples, it's 0 labeled examples. What would you do now? Any suggestions?
You give me the unlabeled example equally for all the classes, like positive and negative. Just give it 0.5, 0.5 out of 10.
Okay, but then I will not be able to learn. Because if it's completely balanced, then I will not learn. Yes?
Could you just initialize a random classifier?
Yeah, that's what I'll do. So think about the 10 example as some initialization. And if my initialization was okay, I can bootstrap from it, right? If the PN and the PV were okay, I can choose good examples. Good example, I mean good labels to the examples and keep on going. And I can do the same thing here. I'm going to initialize. I don't have my 10 examples to initialize with. I'm going to initialize randomly and keep on going. So I'm going to make a guess, continue as above, and this is going to be a version of the EM algorithm that we're going to discuss. Yes?
Wouldn't a random classifier be just as likely to classify them like perfectly wrong and perfectly right?
Yes, it would. And in fact, without adding some assumption, it's not going to work. So the only reason this is going to work is because really there is a generative model that governs the generation of the example, and I'm guessing accordingly. And we'll show that. So in the general case, this is not going to work. But if you have a good idea of what is the probability distribution or what family of probability distribution governs the generation of the data, this is going to work, and in fact it's going to work beautifully because we'll be able to converge to a right probability distribution. So this is where the EM algorithm comes in. So EM is a class of algorithm that is used to estimate probability distribution in the presence of missing attributes. In our case, the missing attributes are the labels. We have the attributes, we don't have the labels. Same thing. Now, it requires an assumption on the underlying probability distribution, and it's very sensitive to this assumption. And also to the initial guess of the parameters, which is very related. So if you believe that you work with one family of distribution, but really the data was generated with another family of distribution, may not work at all. But if you made the right assumption, it's known to converge to a local maximum of the maximum likelihood function, which is good because then you can restart multiple times. Eventually, you'll get a good enough local maximum. So in order to motivate it, I want to play again some coin problems. We observe a series of coin tosses, and we assume that it's generated in the following way. So someone has 3 coins, 0, 1, and 2. The probability of a head in the first coin is alpha, and then P and Q. And the way you observe things is in using the following scenarios. Scenario 1, toss one of the coins 4 times. You observe H, H, T, H. Which coin of the 3 is the more likely to produce this sequence? So there was alpha, P, and Q. Suggestion?
The coin that had the probability of a head that was closest to 0.75.
Yeah. So you see here something that is you estimate to be 0.75. So whichever alpha, P, or Q were closest to 75 is the most likely one to produce this. Scenario 2. First, I'm tossing coin 0. If it's head, I'm tossing coin 1 4 times. If it's tail, I'm tossing coin 2 4 times. What I observe is this, and I'm coloring the first toss in red and the rest in blue. And again, I'm asking you, or this time I'm asking you a little bit harder question. Estimate the value of alpha, P, and Q. So what's your estimate for alpha now?
By 5.
3/5. Why? 3 H's out of 5. Can you estimate P? What do you need to do to estimate P? You have to look only on those groups that start with an H, right? So it's the first group, the third group, the fourth group, and count the number of heads there, right? This will give you an estimate for P, and you can do the same for Q. So again, an easy problem. Third scenario is the same as the second scenario, only that I drop the red character. So you observe the 4 coin tosses in each case, but I drop the information of which coin produced it, whether it's coin 1, the P1, or coin 2, the Q1. How can you estimate the most likely values of P, Q, and alpha now? Okay, so before you answer, that's the question we had, right? So we basically have examples. We don't have the labels, right? So the name of the coin is the label here. I drop this, but I still give you information. Yes?
You could recognize that there's kind of 2 classes here. You have the 3 heads and the 2 heads classes. And you could say, okay, maybe those are the results of alpha being heads and alpha being tails. So you could get an estimate for alpha there.
Right, and in fact, that's what I'm going to do. So, but essentially, what you're suggesting is let's make a guess and try to see if it works. If the likelihood, given the guess, is high enough. That's actually what we're going to do. So just pictorially, that's what we have, right? So we, based on coin 0, we decide which coin to toss, and we use the same coin in this case to toss everything. So the algorithm here is going to be an iterative algorithm, simply because there is actually no, this looks like a very, very simple problem, but there's no analytical solution to this problem in the general setting. Other some additional assumptions, you can come up with solutions. So we don't know how to compute the value of the parameters so that they maximize the likelihood of the data analytically. What we can do is we can write an iterative algorithm, and that's basically what we're going to do. Okay, you know, I think I'm going to stop here because the next few steps are going to be very algebraically heavy, which is too much for today. And I'm going to have to repeat it next time again. So I think with this intuition, there's something for you to think about, and we're going to develop the algorithm next Monday. Questions? Yeah.
I didn't really understand the difference between scenario 2 and 3. Both of them would sit in that way first, toss coin 0 and then undertake such a result.
Yeah, it's the same scenario exactly, 2 and 3. The only difference is what I tell you. So in scenario 2, I give you all the information. I told you in the first sequence, I got head with coin 0. In the second one, I got tail and so on. And because I gave you this information, you can estimate the probability of alpha, P, and Q immediately. In the second scenario, I did exactly the same thing, but I didn't tell you which coin produced the first group, HHHT, which one produced the second one, HTHT, and so on. So it's exactly the same scenario. You know that this group was generated either with the P coin or with the Q coin, but you don't know which one. So the algorithm is going to go like, let's assume a value for alpha, or Equivalently, let's assume that I know which is the label for each one of them, and estimate the likelihood of the data this way. Right? So essentially, I'm going to guess labels, just like in the case of the naive base that we started with, where we moved from the 10 examples that gave us an estimate for the labels to the 0 examples that didn't give us any estimate for the labels. We had to guess them. We're going to guess the labels, and then we're going to use this in order to estimate the likelihood of the data. Now we have labels because we know the likelihood of the data. We can estimate the most likely parameters, and we're going to keep on going. And it turns out that if we use the right distribution, we knew that there is an alpha, a p, and a q. Each one of them has two distributions, either head or tail. We can do well. If, for example, we thought that it's a dice and it can take 6 values, and it so happened that we just saw 2 of the values, h and t here, out of the 6, but we write all the probabilities based on the wrong probability distribution, we're not going to converge. So it really hinges on the fact that we are making the right assumption, but this algorithm actually is going to work. Other questions? Yeah.
Also for the scenario 3, for example, suppose that we have two different maybe clusters. One is a lot of heads, and then the other is the sequence has a lot of tails. But for example, if we have maybe some sequence that the head tails are equal, so when you make a prediction, which group you will put this kind of sample into?
I'm not sure. Let me try to answer and see if that was the question. So, if we are in the extreme situation case where one coin, the P coin, there's probability of head 0.9, and the Q probability of head is 0.1, very different distributions, the problem becomes easier. Because as you try to observe also, it's kind of easier to see that there are 2 classes of examples. And by the way, these are the conditions under which there are analytical solutions here. So if the distributions are very separable, the problem becomes easier. But in general, even in this case, if the P's and the Q's are relatively close to each other, just looking at the data is not going to do it. You'll have to run this iterative algorithm.
Yeah, I mean, like, for example, the 2 coins heads are really different from each other. One is 0.9, one is 0.0. But if we find some samples that has the equal heads or tails, so what can you say about this sequence?
This can happen, right? There is some probability that even if you use a 0.9 coin, for head, you will get the same number of heads and tails, right?
So if you have the samples, which one will be?
So I would use all the samples altogether, and the fact that, you know, in one case I have a more balanced distribution, it's okay. We will see how the algorithm works, and maybe this will convince you. So we're basically computing likelihood, right? So there's no guarantees. But all these are events with non-zero probabilities. Okay, so see you next Monday then.
maybe 9 samples that you have 0.1, and you will use those to predict the alpha, right? So in some of the other examples that have the health and path are maybe similar, so what's the alpha?
I don't know. I mean, so it's not that, as I said, I cannot compute this analytically. There's no way to compute this analytically. So it's an iterative algorithm that will converge to a value for alpha.
Okay, and another question. So what's why the naive Bayes does not reject all the hypotheses?
Say it again.
And you said that naive Bayes didn't represent all the hypotheses.
Yes.
Yeah, why?
I didn't explain why. So you can build examples that show that naive Bayes cannot represent some linear set vectors. Oh, because the way it's computing these coefficients is using statistics over the data.
Yeah, I mean the weight is the sum of probability, right? So the probability cannot be the value in be the average value in the real number, like.
No. So the scenario is going to be something like this. So I'm going to generate some data with a linear classifier, and then I'm going to give the data to naive Bayes. And naive Bayes will not be able to reproduce this linear classifier. It will learn a linear classifier, but not the right one. Because it's basically integer computation, right? So in naive Bayes, the coefficients are some counts, ratios of counts, and it will not get the right number. So I can show you an example. I mean, not now, but in principle, I can show you examples of how this works. It's a little bit hard to explain without looking at an example.
So when can you show me the example?
So in the office hours, I can show you an example.
Okay, thank you so much.
Sure.